Hello everyone, I'm Fei Tang from ICT, Chinese Academy of Sciences. Today I will give you the talk, AIBench Training, Balanced Industry Standard AI Training Benchmarking. These are the other AIBench contributors. I will mainly talk about the following contents: a lack of understanding of learning dynamics raises serious AI benchmarking challenges. AIBench, a comprehensive AI benchmarking project, and AIBench Training Methodology, Workload characterizations, two subsets for repeatable performance ranking and workload characterization, and subsets. Deep learning is a highly dimensioned non-convex optimization program. A slight change leads to a different optimization path, and the AI training heavily depends on the presence for hypermeter tuning. The prohibitive cost of training a state-of-the-art AI model. This is a serious benchmarking challenge. Some mixed processing optimizations indeed improve traditional performance metrics like throughput. However, they adversely affect the final model's quality. We can only observe by running an entire training session, so running an entire training session is mandatory. Unfortunately, it is prohibitively costly, often taking several weeks on a small system. Furthermore, the architectural community heavily relies on simulations, with slowdown varying widely from 10 times to 1,000 times, which further exaggerates the challenge. There are conflicting benchmarking requirements in different stages. On the one hand, earlier stage evaluations of a new architecture or system need affordable AI benchmarks to reduce costs. Meanwhile, affordable benchmarks are also provide valuable performance implications. On the other hand, later stage evaluations or purchasing off-the-shelf systems need detailed evaluations using comprehensive benchmarks to avoid benchmarking. The benchmark's shelf life is short as the state-of-the-art models evolve very fast. However, it often takes more than 1 year to work through benchmark design, implementation, community adoption, and wide-scale testing. A synthetic benchmark like PyroDNN seems useful as it can traverse more neural networks. Unfortunately, it cannot model learning dynamics. An AI task's program scale is often fixed, which raises the scalability challenge. The current benchmarking practice shows the largest scale system can finish an image-led training around several 10 seconds, which cannot constantly stress the system test. HPL AI is scalable, but it cannot model the learning dynamics without considering the model quality. The benchmark mandates being repeatable, while deep learning's nature is stochastic, allowing different but equally valid solutions. The factors of randomness are model initialization, data argument, data shuffle, dropout, and others. AIBench training workloads have different run-to-run variations. Then, I will introduce some related work. Downbench is the first benchmark that proposes time to accuracy as a main metric, which requires training a model to state-of-the-art accuracy. AIBench is the first benchmark that notices the necessity of modeling the critical path of a real-world application scenario. MLPerf is a systematic AI benchmarking project that includes 7 benchmarks for training and 5 benchmarks for inference. MLPerf performs the most large-scale testing, but it fails to present a benchmarking methodology to justify the choices for and opposite AI tasks. models, and datasets. Besides, they fail to consider the conflicting requirements, shelf life, scalability challenges. PyroDN is a first synthetic AI benchmark. The HPLAI is a macro benchmark that uses mixed processing RU decomposition to achieve upper bound flops performance. It is a scalability, but RU decomposition is not relevant to most of the AI workloads. Both PyroDN and HPLAI cannot model the learning dynamics. Next, I will introduce AIBench. AIBench is a systematic AI benchmarking project tackling the challenges mentioned above. It distinguishes and abstracts real-world application scenarios across data center, HPC, IoT, and edge into the scenario training, inference, macro, and synthetic benchmarks. AIBench scenario models the critical path of a real-world application scenario as a permutation of the AI and non-AI models, and each AIBench is an instance of the scenario benchmark suites, modeling end-to-end performance across IoT, edge, and data center. AIBench Training and AIBench Inference cover 19 representative AI tasks with state-of-the-art models to guarantee diversity and representativeness. AIBench Training provides two subsets for repeatable performance ranking and workload characterization to improve affordability. HPC AI 500 is from the AIBench Training RPR subset to evaluate large-scale HPC AI systems, and AIoT Bench is to evaluate various IoT and embedded devices. AIBench Micro provides the intensively used hotspot functions provided from AIBench Training and Inference for simulation-based architectural researchers. As complementary to real-world benchmarks, we plan to provide several synthetic benchmarks with scalable program sizes to modeling learning dynamics. Finally, I will introduce AIBench Training. AIBench Training adopts a balanced AI benchmarking methodology considering comprehensiveness, representativeness, affordability, and portability. Its methodology is as follows. Perform a detailed survey of the critical domain, internet service, including search engines, social networks, and e-commerce. Include as most representative benchmarks as possible. Propose repeatable performance ranking subset and workload characterization subset, and keep the subset to a minimum. Consider the four benchmarks, their subsets, and the macro benchmarks as indispensable. These are three internet service, search engine, social networks, and e-commerce, and their core scenarios and involved AI tasks. There are 19 representative AI tasks selected from three internet services and their models, dataset, and target quality. AIBench Training contains image classification, image generation, text-to-text translation, image-to-text, image-to-image translation, speech recalculation, face embedding, 3D face recalculation, object detection, recommendation, video prediction, image processing, 3D object reconstruction, text summarization, spectral transformer, learning to rank, neural architectural search, advertising, natural language processing. Next, I will detail the workload characterization of AIBench Training. AIBench Training workloads are representativeless and comprehensiveness in many aspects, including algorithm behavior, system behavior, and microarchitectural behavior. AIBench Training workloads also cover many different networks like CNN, ResNet, RSTM, GRU, Attention, and others. It also contains workloads for different data types, including text, image, audio, video, and 3D data. Among the architectural independent metrics, AIBench Training covers more range than Perf Training in flops, parameter size, and conversion rate. Among the architectural dependent metrics, including computation pattern and memory access pattern, AIBench Training is more diverse than Perf Training. AIBench Training and Perf Training are concurrent but work. AIBench Training has more diverse workload characterizations. Among the AIBench Training workloads, there are different workload characterizations, and all of the workloads are different. Then I will describe the subsets for repeatable performance ranking and workload characterization. We have the following requirements for selecting repeatable performance ranking subset, reflecting diverse model complexity. Widely accepted evaluation metrics. For the workload characterization subset, we select the minimal workloads with the most representative system or microarchitecture characteristics. Finally, we choose image classification, object detection, and learn to rank as a RPR subset. We use k-means to cluster all the workloads from the AIBench Training and find that they are clustered into 3 different clusters. For the WC subset, we choose the most center workloads from 3 clusters. They are spectral transform, image to text, and speech to text. At last, we find some insights from AIBench Training RPR subset. We use the AIBench repeatable performance ranking subset to rank the performance of GPUs and TPUs listed in the table. AIBench Training covers more hotspot functions than Perf Training, which is more suitable for simulator research. TPUs have significant performance advantages in image classification, but lack generality and do not support many models, like fast RCN and learn to rank, because they support limited TensorFlow operations. PyTorch is poorly optimized for TPUs because it cannot load data directly from Google Cloud Storage onto the TPU as TensorFlow does, and data loading is a bottleneck for the image classification task. At last, I summarize this presentation. First, I introduce some 5 AI benchmarking challenges: prohibitive cost, conflicting requirements, short shelf life, scalability, and repeatability. Then, I describe AIBench, our comprehensive AI benchmarking project. Finally, I detail the AIBench training methodology, workload characterizations, 2 subsets for repeatable performance ranking and workload characterizations, and insights. Thank you for your listening.